I would like to talk about this subject, which is my which has been the subject of my research, M-theory and exact solution of gauge theories. So this is going to be a very elementary introductory talk. Microphone is not.
It is not, but the direction is very bad. So this is the theory 7, so I can't help you.
Yeah, so it's a very introductory seminar. It doesn't involve too much of my own work or a heavy formula. I would like to begin by what the M-theory is. But in order to talk about the M-theory, I would like to start from the history of string theory and in particular its second revolution. Right. So as you know, superstring theory is one of the promising candidates for the theory of everything. And the basic idea for the string theory is very simple. All the elementary particles are not points, but strings. So as this figure shows, there are two different kinds of strings. One is closed string and the other is open string. Okay? And then both strings are of this very, very tiny scale. So this scale, length scale, that's called the string scale, is about 10 to the minus 35 meter. So it's a very, very tiny object. Okay? And we describe the motion of these open strings and closed strings using two-dimensional quantum field theory defined on the world sheet of these objects. So this is the basic definition. And starting from this simple idea, the string theory proposes the unification of particles and forces. And according to string theory, different particles can be regarded as different vibrational states of a single string. So this is just a cartoon, but the idea of string theory is to try to explain all the different kinds of particles known in nature in terms of different vibrational state of a single string. Okay? And in the mid-1980s, 5 different superstring theories were found, and those theories are called type 2A, type 2B, and type 1, and 2 heterotic string theories with different gauge groups. And these 3 lines are, 5 different theories are classified according to the supersymmetry in 10 dimensions. So this has n equal to 2A supersymmetry. This has n equal to 2B supersymmetry. And all these others are characterized by 10-dimensional n equal 1 supersymmetry. Anyways, there are 5 different superstring theories found in mid-1980s. Okay? And in order to calculate the scattering amplitude of particles in string theory, what we do is instead of summing over Feynman diagrams and integrating over the internal momenta, what we do is to summing over the different topology of the string world sheet. The topology is characterized by the number of handles for the world sheet. The number of handles is H. H is called the genus of the Riemann surface. So we sum over the topology of the Riemann surface, and in addition, we have to integrate over all the different shapes of the Riemann surface of a given topology. And the genus H surface is multiplied by the string coupling GS to the power 2H minus 2. Okay, so this is basically how we compute the scattering amplitude of particles using string theory. Okay, and the structure of the moduli, the space of shape of the Riemann surface is very special, and also we have introduced the length scale so that this summation and the integration is believed to be free of UV divergences. Okay, so this is how we believe the superstring theory to be a consistent theory of the quantum gravity. Okay, but at the same time, maybe you can imagine that as the genus increases, the integration over the different shape of the Riemann surface becomes more and more complicated. So if the string coupling is not very small, we have to care about the integration of all the different shape of the higher genus Riemann surface, which is very, very complicated. So there is always a difficulty in this definition of the superstring theory regarding the strong coupling dynamics. Okay. So strongly coupled strings were very difficult to study. We believed so until the mid-1990s, but there was a big breakthrough in the mid-1990s where many non-trivial quantum equivalence relations between many different superstring theories were found. Okay, and those quantum equivalence relations are called duality, and the duality is quite typically something like one strongly coupled string theory being dual or equivalent to another weakly coupled string theory. Okay, so thanks to the discovery of many such relations, our understanding about the superstring theory was a lot improved. So thanks to the discovery of various superstring duality, those 5 different, seemingly different superstring theories were found to be connected to one another into something like this, a single web-like object. Okay. And even more interestingly, at the corner of this duality web, there is an 11-dimensional theory appearing. And this is the definition of the M theory. And this is what the M theory is. So in more detail, M theory was first found by Edward Witten in 1995, and this is discovered as a strong coupling limit of what is called type 2A superstring theory. So if we increase the coupling of type 2A superstring theory, then it turns out that 11th dimensions start to emerge. And this 11th direction turns out to make a circle of this radius. The 11th dimension is a circle of this radius. The radius is the product of G string and string coupling and string scale. Okay, so here is a picture how the M theory emerges out of the strong coupling limit of type 2A string theory. So the type 2A string theory is a 10-dimensional theory, and this is a theory of a string. And if we increase the string coupling, then we start to be able to see 11th dimension, which is a circle. And what is more interestingly, the type 2A superstring turns into a membrane, which is actually wrapping on the circle, 11th direction. So if we limit ourselves to the very, very weak coupling problem, then actually this 11th direction is very, very small. So that what is actually a membrane looks like a string. Okay. This is more or less the relation between type 2A and the M theory.
So are you saying that in a strong coupling limit, you have 11-dimensional theory becomes 10-dimensional because the R11 is small?
When G string, the coupling constant of type 2A superstring theory is very weak, we cannot see this 11th dimension because 11th direction is very small. Okay. Okay. Right. So this is one characterization of M theory, but this is far from the definition, I think. So M theory as yet has no intrinsic definition, like the definition of superstring theory in terms of summation over the world sheet. But we know some of the characteristics of M theory. The first important property is that the only parameter in the M theory is a Newton constant, or the 11-dimensional Planck length. Okay, LP is the Planck length, and in terms of LP, 11-dimensional Newton constant is defined like this. Okay. Aside from this dimensionful constant, M theory doesn't have any variable, continuously variable coupling constant. So in this sense, M theory is regarded as ultimate theory. And another important characteristic is that at low energy, M theory is believed to reduce to 11-dimensional supergravity. Okay? And since this M theory is a quantum theory of 11-dimensional supergravity, we know that there are some fundamental objects which have 2 plus 1 dimensional world volume extension, and which is called membrane. And also, we believe that there are 5 plus 1 dimensional objects called M5. Let me explain this point in more detail. Well, the low energy limit of M theory is 11-dimensional supergravity. So in supergravity, we know there are metric and its superpartner gravitino, and in addition, we know that there is a gauge field which has 3 vector indices. And actually, this gauge field is totally anti-symmetric with respect to this index. So this is free-form potential. And let me denote the derivative, the field strength of this potential by F. And then the supergravity is defined by this action integral. The first term is the famous, the familiar Einstein-Hilbert term. And in addition, we have a kinetic term for the gauge field, and this is a very interesting topological chance cycle. Okay, so since we have the 3-form gauge field, the natural object that electrically couples to this 3-form gauge field is a 2 plus 1 dimensional object. And this is an electrically charged object with respect to this gauge field. This is membrane. And if we have electrically charged object, then we can think of a magnetically charged object as well. And it turns out by a simple dimension counting that magnetically charged object has 5 plus 1 dimension. So this is more or less the definition of M5. Okay? So since we know the existence of this gauge field, we know the existence of membrane and fiber. Okay. And in fact, in superstring theories and M theory, we know, or we believe there are many other dynamical objects other than string, and those dynamical objects has various different dimensions. And we call those objects as branes, which is a generalization of the word membrane. And we call p-brane those objects which have p plus 1 dimensional space-time extension. Okay, here is a table of the spectrum of branes, which is known to exist in type 2B theory, type 2A theory, and M theory. Okay, we have this many branes. And here we have string, which is a 1 plus 1 dimensional object. But in addition, we have D particle, D string, and many others. Okay. So after the discovery of string duality, we have found many such objects, and it turns out that we have to study the property of each of these objects. Among those different kinds of branes, it turns out that this DP brane, those objects called the D branes, are very easy to study because the excitation of D branes can be just described by the motion of open string attached to the brane. D branes are characterized by the property that open string can have endpoints. And we studied the dynamics of open strings attached to them, and then it turns out that the D brane, the dynamics of D branes are described by just a p plus 1 dimensional supersymmetric gauge theory. And in addition, another interesting property is that if n of the same D branes are put together, then the gauge symmetry enhances from U1 to Un, non-abelian gauge symmetry. Right. So after the discovery of string duality, we became particularly interested in the relation between the dynamics of D branes and the supersymmetric gauge series. Okay, and in fact, those two subjects are have been developed under a very strong mutual influence. Okay, let me move on to this subject, and yeah. Are there any questions? Okay. So the first interesting thing about the connection between the brane dynamics and gauge theories is that we can actually use the construct of branes to realize various different kinds of gauge theories. So today I would like to talk about three particular examples. So in 4 dimensions, we have supersymmetric Yang-Mills theory with various amount of supersymmetry, n equal 1, 2, 4. Okay, let's try to construct these different theories using grains. Okay, the first one is n equal 1 supersymmetry. In this theory, we have vector field and its superpartner spinor. Okay, and the vector field is known to have 2 on-shell dynamical degrees of freedom, and the spinor has also 2 on-shell degrees of freedom. So there is a match between boson and fermion number of degrees of freedom, 2 plus 2. So this is n equal 1 super Yang-Mills. So n equal 2 super Yang-Mills has twice as many spinor fields as n equal 1. So we have 4 fermionic fields, but the gauge field gives rise to only 2 bosonic degree of freedom. So we have to add 2 fermions in order to get the matching between the number of bosonic fermion degrees of freedom. Okay? So this is the spectrum of fields for n equal 2. And finally, in n equal 4, we have 1 gauge field and 4 fermions and 6 scalar fields. Okay? The number you can work out very easily. Given the number of degree of freedom for gauge field is 2, spinor 2, and then scalar 1. Okay. Right. So in 4 dimensions, we have this many different super Yang-Mills theories. So how to construct these different theories using grains? Well, first of all, n equal 4 super Yang-Mills can be realized on just a parallel D3 branes. D3 brane has 1 plus 3 dimensional world volume, and on this world volume, 4-dimensional cell is living. Okay. So this table shows in which direction the D3 branes are extending along. D3 brane is extending along 0, 1, 2, 3 direction. So the remaining 6 directions are transversal direction. And actually, I said that in n equal 4 super Yang-Mills, we have 6 scalars, and these 6 scalars can be obtained as the transverse coordinate of this D3 branes. Okay. In n equal 4 super Yang-Mills, we have 6 scalars. This corresponds to the fact that D3 branes has 6 transversal directions. Okay. And actually, if we look into more detail of the UN n equal 4 super Yang-Mills, then we have 6 scalars, and these 6 scalars obey this potential, which is basically the square of the commutator. Okay. Then if we are interested in the vacuum, the vacua are characterized by as the minima of this potential, and then it is very easy that at each of the minima, phi I and phi j have to be diagonalizable simultaneously. Then in a suitable gauge, all these phi n by n matrix has to be diagonalizable in this way. And these n diagonal components have a natural interpretation as a position of the D3 branes in the transverse R6. Okay, n objects are moving in the 6-dimensional space. So, so this is a very nice example where the gauges, the quantities in the gauge theory and the dynamics of brane are related. Okay, let's move on to the less supersymmetric example. So n equal 2 supersymmetric Yang-Mills. So this theory is known to be constructed using D4 branes and NS5 branes in type 2A supersymmetry. Okay, D4 branes are extending along this 0, 1, 2, 3, and 6 direction, and NS5 extends along 0, 1, 2, 3, 4, 5. So this is, roughly speaking, a picture. Okay, so in this case, as I said, there are only 2 scalars. Okay, the interpretation is that since D4 branes are suspended between NS5 brane, the only direction where the D4 branes can move is along 4 and 5 directions. Okay, this is why only 2 scalar field. Okay, very easy. So let's look at n equal 1 super Yang-Mills. this Yang-Mills theory can also be constructed by using type 2A branes, D4 branes and NS5 branes. But as compared to the previous example, one of the two NS5 branes are rotated. Okay, now one of the NS5 branes are extending along 0, 1, 2, 3, and 8, 9 direction. Okay, and the remaining two kinds of branes are the same. Then, as you can see from this figure, this blue guy cannot move in any direction. That explains in n equal 1 supersymmetric Yang-Mills, we don't have any scalar. Okay? Then, yeah, so up to now, the story is very easy. Just drawing some orthogonal intersection of branes and read off the particle spectrum at weak coupling. Now let's see what happens at the strong coupling regime of the gauge. Actually, the D brane can say a lot about the strong coupling dynamics of the gauge. Well, so let's start with n equal 1 supersymmetric Yang-Mills. So there are a few known facts about this model. First of all, although this super Yang-Mills is a theory of massless gauge field and massless gauge at low energy we don't observe the massless particle. The theory is mass gapped. Okay, and also in this theory there is a chiral symmetry. The chiral symmetry means a symmetry which rotates the gauge by a phase. Chiral part of the gauge rotates in one direction and the anti-chiral part rotating in the opposite direction. And this kind of chiral symmetry is anomalous. So anomaly-free chiral symmetry is Z2n, but due to the choice of a vacuum, this chiral symmetry is broken from Z2n to Z2. And in relation to this, this theory is known to have n distinct vacua, and those n distinct vacua are all labeled by this n distinct choice of the phase factor. So this is the non-zero value of the gauge bilinear condensate. So there are n different choices of the phase factor. Okay. So let's try to understand this n distinct vacua using the brane construction. Okay, you remember what is the brane construction for n equal 1 super Yang-Mills. So this is the situation at the very weak coupling. Okay, so this is the type 2A brane coupling, brane construction. So we want to know what happens at the strong coupling. Okay, to understand this, what do we have to do? Well, what we have to do is to move from type 2A to M theory, because M theory is a strong coupling limit of type 2A. Okay, what happens? Well, the answer is that this type 2A brane construction transform into just one smooth M5 branes. Okay, the reason is that in M theory we only have 2 branes and 5 branes. We don't have 4 branes. Okay, so we start from this brane construction, and we have to get something which is made only of 5 branes. Okay. Then the next question is, what is the precise mathematical shape of this guy? Well, the shape is known to be described by complex variable, because this object has to preserve supersymmetry. Supersymmetry and homomorphy is very much related to each other. Okay, in order to describe this complex shape of this guy, we introduce 3 complex coordinates. V is x4 plus I x5. Essentially, x4 and x5 are the coordinate along this purple guy. Okay, as you can see this from this figure. x4 plus I x5 is V, and x8 plus I x9 is W. So this is the coordinate along the green guy. And finally, x6 plus I x11 exponentiated is T. So this is essentially this x6. Okay. Now, this part, the purple part of this M5 brane is characterized by T equal V to the N. Okay. the argument which leads us to find this equation is as follows. So if there is no D4 brane here, this purple guy is just standing flat. Then NS5 brane just standing flat corresponds to T equals constant, because the 5 brane stays constant in the T direction. But if you provide N D4 branes, then that NS5 brane gets pulled. And this drag force is expressed by this very simple homomorphic equation. And secondly, this shape of the green guy is also described by this very simple homomorphic equation. Okay, and our task is just to connect these two complex equations. But it turns out that there are n distinct ways to connect these two equations. As you can see, from this and this equation, the natural equation we would get is v times w equals constant, but this constant has to be n root of zeta, and there are n distinct choices for that zeta. So this is very nicely related to the fact that in n equal 1 superunions, we have n distinct choices for the vacuum. Okay, clear? Okay. So let's move on to the second example. In n equal 2 supersymmetric amines, so let's choose the gauge group to be SUN. Okay, so in this theory, like the previous example with n equal 4 supersymmetry, we have a scalar field, actually 2 scalar fields, and those 2 scalar fields obey this potential.
I'm sorry. So in the strong and the weak coupling leaving the vacuum structures are different.
Coupling, zero coupling and finite coupling are different.
Okay, the vacuum are different.
Yeah. You mean n equal 1?
Right, the previous.
Yeah. Yeah. Okay, so continuing this example, the potential for 2 scalar fields is this, and then again, phi and fiber have to be simultaneously diagonalized. So at generic vacuum, the phi looks like this. Okay, and as we will see, this A1 to AN corresponds to the position of the D4. Okay, so we have many degenerate vacua, and those degenerate vacua are parameterized by n-1 complex parameters, A1 to AN, and since we are thinking about SUN, the sum of A1 to AN has to be 0. Okay, and at generic vacuum, the gauge symmetry, originally we started from SUN, but generally gauge symmetry breaks down from SUN to U1 to the n-1. So at low energy, the only light degrees of freedom are n-1 copies of photons, electromagnetic fields, and their superparticles. Okay, all the other particles acquire masses, and those masses are, roughly speaking, proportional to the difference of AI and H. And in this situation, an interesting problem is to compute the electromagnetic couplings for n-1 copies of electromagnetic fields. This is one interesting problem. Another interesting problem is to compute the mass of charged particles, which carry electric and magnetic charges under this U1 to the n-1 gauge symmetry. Okay, and these quantities, electromagnetic couplings and the mass of the charged particles, are going to be both a function of A1 to the AN as well as the dynamical scale of the superunions. Okay, that's the problem. And this problem is what is called the Seiberg-Witten problem. So the solution to this problem is called the Seiberg-Witten solution. Seiberg and Witten in 1994 solved this difficult problem by introducing a rather technical, mathematical object called the Seiberg-Witten curve, which is just a Riemann surface, in this case of genus n-1, whose shape varies as a function of this vacuum choice parameter. Okay, so let's try to reproduce this solution using plane construction. Well, as I said, we start from type 2A, and we consider this plane construction. D4 branes, n copies of D4 branes are